Good day, ma'am. I am Maria Guerati Cabusag, and you will meet my partner later, Miss Lawrence Dian Dococo. And we are going to present our performance innovative task in OR1 using linear programming and Excel solver in transportation problem. We chose this problem because, as we observed, business is the new trend in today's generation, where everyone think or came up with possible business to build, do, or propose. This is also to promote business supporting local products, where it is possible to buy local products on different locations and transport it. This problem is only small range in distance, yet could also work for long range transportation and shipments. So our problem is Hardin Furniture had two branches which are located at Katarman and Sagay that supplies local furnitures in the island with a number of supply of 50 and 80 respectively. These furnitures will be transported to its distributors located at Bunbon, Mambahaw, and Yumbing. Suppose that the destination of three distributors demanded 10, 25, and 18 units of products respectively. The cost per peso of transporting the furnitures from the two branches to the three distributors will be given on the table. The table shows the cost of transportation from the branches to the distributors. On the left side column, you can see the number of supply, and on the right row in the table is the demand. So our problem is to determine the optimum distribution of the transportation to minimize the total transportation cost and how much is the cost. Now we have here the transportation network for this problem. The circle represents our nodes. The right circles are the two branches and the left circles are the three distributors or our destination. The arrows from the branch to the distributors is called the arcs. From node C are the transportation cost from Katarman to the distributors, and node S for the cost from Sagay to its distributors.
We are going to construct the LP model where our division variables are: let XC1 be the number of furniture from Katarman to Bunbon, XC2 be the number of furniture from Katarman to Mambahaw, XC3 be the number of furniture from Katarman to Yumbing, XS1 be the number of furniture from Sagay to Bunbon, XS2 be the number of furniture from Sagay to Mambahaw, XS3 be the number of furniture from Sagay to Yumbing. Xij be the number of units from the branches I to distributors J, where I equals C Katarman and S Sagay, J equals 1 Bunbon, 2 Mambahaw, and 3 Yumbing. Our objective function is to minimize 20xc1 plus 50xc2 plus 45xc3 plus 35xs1 plus 70xs2 plus 80xs3. And our functional constraints are subjected to supply constraints xc1 plus xc2 plus xc3 is less than or equal to 80, and xs1 plus xs2 is less than or equal to 50. In demand constraints, xc1 plus xs1 is greater than or equal to 10. xc2 plus xs2 is greater than or equal to 50. And xc3 plus xs3 is greater than or equal to 18. And our non-negative constraints is xc1 plus xc2 plus xc3 plus xs1 plus xs2 plus xs3 is greater than or equal to 0, or xij is greater than or equal to 0.
Using this Excel solver, we obtained that the total transportation cost is 2,305. And the table shows how many units of product will each branch transports to its distributor. In the sensitive analysis, we have here the optimal solution, which is represented by the final value. The allowable increase and decrease value specifies how much the objective coefficient could change before the optimal solution will change. Now, the bottom part of the table titled Constraints addresses the range of feasibility, that is, the range of the right-hand side of the constraints, with the shadow price remains unchanged. Example, as long as the right-hand side constraints in unit demand of Bonbon is between 87 and 7, the shadow price of 35 will apply. Shadow price refers to the amount of change in the optimal objective function value per unit increase in the right-hand side of the constraints. If you have something to change in the current values, you need to resolve the model. And this ends our presentation.